Good morning, one and all, physics students, to another episode of Mr. Finn's Physics. This is for regular physics for March 24th, Tuesday of 2020. Hope everybody's doing okay out there. Had a couple questions. One question came in regarding what happens to the circuit or the current in the circuit when the number of batteries changes. So we're going to go over that in a little bit. And first, I'm going to take a quick look back at the power values. So another look at power from yesterday, and we'll wrap that up and then take a look at the question for today. Before we do that, though, we want to make sure that some of these responses are going to Google Classroom. So I'll be grading in Google Classroom for the entire time that we're out of school. If you are behind, just find a way to catch up. You know, you have your spring break coming up next week. Make sure you get to all the lessons. At the end of this week, I'll have a Google Form quiz ready for you so you guys can test yourselves on how you've done with all of the video content to this point. So I'll try to get that ready for Friday of this week. Just look for that. I think we'll probably make that available from by 11 a.m. until about 1 p.m. on Friday. So make sure you guys check that out and give yourselves a little chance to review some of the material we've had so far. So, looking back at power from yesterday, let's go back to our big white magic board here real quick. Okay guys, we're back here at the big magic white board here. Let's talk about a couple actual applications of power. Yesterday we learned that power was current times voltage, and that's always true. Remember, we can always use Ohm's law as well. V equals IR. So what does that do for us? It allows us to see a couple of different neat things in case we don't have all the variables we need at the moment that we're using them. For example, up here you got power is current times voltage, which we learned yesterday. But V equals IR, Ohm's law, which we learned a few days ago. If you combine those two, subbing IR in for the V of this equation, then you get a real quick substitution. P equals I, and instead of V, we're subbing I times R from Ohm's law. So what we get is P equals I squared times R. It's just the two I's multiplied together, multiplied by the R. So if you have the current and you know the resistance, you can find the power dissipated by that circuit or by that particular resistor in terms of energy per time. Similarly, we can use the substitution in reverse order. So instead of I, why don't we use V divided by R? Because that's right from Ohm's law. So if we use V divided by R in place of I, and we sub it back into the power equation, remember V over R substitutes for I, multiplied by V, and we're going to get V squared divided by R. So these are pretty common applications of power, but they all mean the same thing. It's still going to come out to be the amount of energy per time, or the number of joules per second used or consumed or dissipated in a certain circuit. Hope that helps. Okay guys, so what do we have here? The same setup we had the other day, but instead of the one battery here, I have two batteries. And you'll remember this is an S-shaped system. So I'm just going to connect the springy part with the bottom of the battery and the top of the battery to this knob part right here. So when I put that second battery in, the input is here and the output is right here. So that's input and then output on the next spring on the other side. So this is the difference between yesterday and today, where I had one battery going. Now I've got two batteries going. And you remember this bulb. This is the round bulb. Well, we had two values for resistance. One was 10.5 ohms and the other one was 31.5 ohms. So if I connect this circuit, I'm actually reading about 206 milliamps. Now if you remember, this value for this bulb yesterday yielded a current of about 144 milliamps for the one battery circuit. Now if you don't remember that, let's just take one battery out there and we'll hook it up like this. And there we get about, well today we're getting about 141. So about 141, 142 in terms of milliamps. Okay, so let's go to the big whiteboard and check that out. Okay, guys, we're back. Yesterday, we found a value of about 144 milliamps. 144 milliamps for that 10.5 resistor bulb. Remember, this was the round bulb. So here's what we have. V divided by R is equal to I. So yesterday we found the value of one bulb to be 10.5 ohms. So 1.5 divided by 10.5 ohms would actually give us about 144 milliamps. That was the reading on our current meter yesterday, our ammeter, which was dialed in for current. Today it's reading about 141 milliamps, so I may have lost a volt or two, or not a volt, a few fractions of a volt on that battery. Or maybe I used a couple of different wires and different resistance. But either way, today, all we're trying to do is double the voltage by using one extra battery. That should double the current because this relationship is a direct relationship. The resistance isn't changing because I'm still using the same round bulb. But what happened today? Today, we had 3 volts divided by the same 10.5 ohms. And I should get about 288 milliamps. That should make sense because we're doubling the current if we double the voltage. But what did I really get today? I really got 208 milliamps. The difference is about 25%. If you take about 0.208 in terms of amps and you subtract 0.28 and then divide by 0.28, remember this is our formula for percent error. Observed minus accepted divided by accepted times 100%. If I take that and find a percent error, I'm actually coming out with about 25% error. So what's the deal? What happened? Where did the changes come from? Okay, guys, what did you think? Where did those changes come from? I mean, 288 milliamps to 208 milliamps. That's kind of a difference. I wonder what the problem is. Well, we had the same round bulb. We had the same battery. But what we did do was we added a second battery. Now, this second battery might not be the rating that's on the battery. You see, it says 1.5 volts. But what if that battery is a little older and is not operating with 1.5 volts? What if it's only putting out 1.3 volts? That would make sense, that the current would be less than what you would get if you had those batteries brand new, or if the batteries themselves didn't offer any resistance to the system. That's something we didn't consider. Everything in the circuit is going to have a little resistance. If you don't remember that, go ahead and view my video on piece of resistance to make sure that you're up to date on the things in a circuit that can actually have resistance. So today, we have a round bulb that doesn't give us exactly the same values that we got from yesterday. What do you think the long bulb would do? Let's do a quick look at that to make sure maybe there's a little bit of a better value for the long bulb rather than the round bulb. Let's take a look at the long bulb right now. Okay, guys, we have the long bulb installed here. And yesterday, we calculated a resistance of about 31.5 ohms for the long bulb. 31.5 ohms. By using the current value, it came out to be about 0.095 amps. So now, I've got my same 3-volt system here. We think it's 3 volts. And we're going to hook this up. So my long bulb is lit, and my meter is running. And you can see the meter gives us a value of about 68.9 milliamps. 68.9 milliamps. Okay, so let's take a look at what this long bulb would be with just one battery inside. 68.9 with 2, therefore one battery should be about half of that, should be about 34. And we're not getting 34, we're getting 48, about 48 milliamps. So 48 milliamps to about 68 milliamps is a bit of a difference. Let's go back to the magic board and check it out. Okay guys, we're back again at the magic board. Let's check out our data for the long bulb. Today, we had 1.5 volts divided by the 31.5 ohm that we discovered the long bulb was yesterday. And we got the same data, about 0.0476 amps, or 48 milliamps if you move the decimal place 3 places. 48 milliamps is the current through one of the long bulbs with one battery. The actual reading confirmed that at 48 milliamps. But what happens when we add another bulb? Another battery. 3 volts divided by 31.5 ohms, assuming that's the same resistance, and we got 0.095 amps. We should have got right around 95 milliamps just by adding a second battery. But what did we really get? We really got 68 milliamps. Now that's less than 95, but if we take 68 and compare to 95, we know we're going to have a lot less current there because of the extra resistance. Now where did this extra resistance come from? If you look at the circuit, maybe the voltage that you're adding is not exactly 1.5 volts. Or maybe 2 batteries provides a significant amount of resistance than 1 battery. Either way, guys, we know that the actual values might not be as close to the theoretical values that you think using Ohm's law. Hope that helps. Okay guys, what did we learn today? Well, number one, we had those 2 extra ways to look at power. I squared times R, or V squared divided by R, will still give you power in watts for that circuit. So if you know those 2 variables, you don't have to use Ohm's law to solve for the third. You can go straight to power definitions. Secondly, we took our circuit that we learned yesterday and we hooked up another battery, basically increasing the voltage by a factor of 2. Well, it didn't really turn out that way though, because what I should have got was twice the current, and I didn't get twice the current with either the long bulb or the round bulb. Okay, so that means that the lab values are going to be slightly changed from the theoretical values. Stay tuned, guys. Tomorrow we're going to look at some other things by moving some other bulbs around. I'm going to introduce you to the fact that we're going to have some circuit changes. So there could be some brightness values that we're going to have to determine. Make sure you guys are keeping up on the videos, and we'll have a Google form quiz at the end of the week. And all the grades we have now are going to Google Classroom and not to MyStar. So when we get the final determination from the district about what we're going to do for the rest of the year, we'll be able to touch base and give you guys a little chance to make up for lost credit, obviously, and to demonstrate your new knowledge. Remember, we want to make sure we can, at the very least, test out of physics by the end of the year if we end up not coming back to the end of the school year. Well, that should do it. I hope you guys are okay with Ohm's law and power, another application of that, and we'll be back tomorrow to give you some more information regarding electric circuits. Have a great day, guys, and we'll see you tomorrow.